Hello, everyone. I guess we'll just start. This is the first NCS 2030 webinar. And today, Viktoriya Yarushina holds the presentation. She's the department head for reservoir technology at IFE, and also a work package leader in the National Center for Sustainable Utilization of Energy Resources. She is also a work package leader at the National Center for Subsurface Well Integrity, Plugging and Abandonment, the SFE SWEPA. She has a PhD in solid mechanics and the physics of geological processes. Before coming to IFE, she worked at Yale University and University of Oslo. Her research interests focus on coupled fluid flow processes, chemical reactions, mass transfer, and deformation in the subsurface, with applications to the energy transition, CCS, P&A, and hydrogen storage. Her research involves a range of approaches from experimental work through chemical and isotopic analysis to numerical simulations. So, Viktoriya, if you are ready, you can go ahead with your presentation.
Yes, thank you, Shasti, for introduction. And while people are still connected, I just got several people knocking on my door asking how to connect. So I assume that some more people will join. We will start with Mentimeter. So I will ask all of you, go to menti.com. You can do it on your iPhone, for example, and use this code that you see here. So let us get to know each other. Who are we joining the webinar and who are we in the NCS Center? So I see people already started to vote, 3 votes. Students are here. That's very nice. So we have quite a broad spectrum of participants today. So most of us researchers, but I'm very glad to see that not only researchers from the center are present today. Very nice to see PhD students, engineers, and some other people who expressed interest in our webinar. So today I will be talking about predicting fluid migration pathways and dynamic flow localization in the subsurface. This is work that we did together with a lot of colleagues from IFE, Lawrence von Liang-Wang, René van Noort, then my colleagues from oil company MOL Norge, Gabar Koshitz, then people from small geophysical company in Netherlands, and also my colleague from University of Oslo. So the next question to you, what words come to mind after hearing fluid migration? So let us see. So let's ensure that we are on the same page. Can you please go back to the Mentimeter and just type 3 words that come to your mind when you hear these words? Do we have results already? Are you able to come to the Mentimeter? It seems that something is not right. Okay, we just jump over. Ah, there you are. You see so many different words. Leakage, yes. Charge, yeah, leakage is the negative part, charge is positive. Dynamic heterogeneity, of course, heterogeneity is important. Yes, it needs understanding. And with big words, we see those which appear most often: fracture, flow, and permeability. Yes, permeability is of paramount importance. Okay, let's see what is localized flow. What does it mean and where it occurs? It happens in all the places in Earth, and the importance of fluid flow in general on Earth is difficult to overestimate. Even Earth's core and mantle contain melt that moves through the porous network in pretty much the same way like oil moves through pores in the reservoirs, creating mantle convection and generating the Earth's magnetic field, which actually protects us from cosmic radiation and makes the life on Earth possible. And as melt moves, it creates mantle plumes that you can see here as this yellowish channels. And what's interesting that this melt also rises to the surface in form of this quite narrow channels. So this is a schematic picture from one of the Nature articles that shows how melt from core can move up through the mantle. And yes, it can be possibly large plumes like that, but most probably it's still these small narrow channels which are showed in the first image here. And when mantle moves upward, when it goes to the crust, it melts the rocks in the crust, and it creates so-called hotspots. And you all heard about those, maybe not this precise word, but you all know Hawaiian Islands. You all know Iceland with its hot springs. And all of that because of the hotspots, which are caused by focused fluid flow. And Hawaiian Islands by themselves, they were formed actually by the localized flow of magma. Plate tectonics, what it does, it moves the plate above these hotspots, which stay more or less on the same place. And that's how these islands created. So when plate moves further, the island stops being volcanic and just solidifies, and it creates the usual island. And more examples of this focused fluid flow. Focused fluid flow is also visible as, for example, the spectacular features on Earth. It creates a dike and sill complexes that look approximately like that. And this is how they look in the surface. This is a fantastic example from Shiprock Dike Swarm in New Mexico. And this example, this dike and sill complex, is from Franz Josef Land, but we can see quite similar dikes and sills also in Svalbard. So this is the whole dike swarm. And this map shows here's the Franz Josef Land and here's Svalbard. So this is the same dike swarm. So there are multiple dikes shown in with red color. And all of them actually a result of focused flow of magma, which was liquid one day. And going more shallow into the subsurface, we also see focused fluid flow. And it can be expressed as sand injections, which you can see on the surface, look like that. It can be faults, and multiple faults shown in this schematic picture. And this is how they look again on the surface. And it can be pop marks on the seafloor, which look like these dots on a huge seafloor. But how do we know how fluid moves in the subsurface? How do we discover it? One thing is what we see on the surface, another thing, what is really happening down there. So there are several methods, and one of them is tomography, a method that is also used in medicine. So when you go and do tomographic study, so it's pretty much the same procedure as geophysicists use to study what is inside the Earth. It uses penetrating waves to produce an image. And this is an example of fluid ascent at Mount Spur volcano in Alaska. And these finger-shaped anomalies, they indicate fluid pathways from deep crust to shallow depths. And these different colors, they actually indicate the ratio of VPVS velocities that are very sensitive to the presence of fluids. These fingers are filled with liquids and melts. And interestingly, in this case, that fluid ascent is also accompanied by seismicity. These yellow dots are earthquakes. And this is this figure is more or less data obtained from seismic tomography. And this is an interpretation that was done by geophysicists later on. The method that is very commonly used is multi-channel seismic reflection. The principle of this measuring method is the transmission and reception of seismic waves, like an ultrasound examination performed by a doctor. And here is an image from dike and sill complex in the northern Barents Sea, the same dike and sill complex that I showed you before. Here, vertical and related horizontal seismic anomalies like this one, like this one, like this one, or horizontal like this one, they were interpreted as dikes and sills. In seismic data, focus fluid flow is often imaged as near vertical zones of highly attenuated chaotic reflections called chimneys or pipes. In many cases, chimney structures are rooted in petroleum generating source rocks and gas or oil-rich reservoirs and act at the seafloor to form craters or pop marks, often associated with active degassing. For example, like here, this is a Swiss lake where giant pop marks were found not so long time ago during just the usual regular cruise. It was a PhD student who had worked that day, and she was really, really surprised with what she saw on the seafloor. So they saw these craters, which you can see around 100-meter wide, maybe a little bit more. And here, even more than 100 meters, several pop marks, one in the one is superposing another one. And when they shot seismic, they saw that these pop marks, they are also associated with seismic chimneys. So seismic chimneys always end up with pop marks. And in this case, you can see even some traces of active water expulsing from the pop marks. In this case, pop marks are caused by groundwater discharge. But in the Northern Sea, often chimneys are associated with reservoir leakage or with gas hydrate leakage. And why do we care about seismic chimneys? Well, first of all, they indicate movement of fluids through different geological sequences. And these fluids can be oil or gas very often. Recently, seismic chimneys have been used as one of the key hydrocarbon indicators in petroleum exploration. For example, in 2013, Roar Hegland of Equinor evaluated 100 drill traps in the North Sea and found that the success rate for drill traps with no chimneys is less than 50%, while the success rate for drill traps with chimneys is above 80%. But this is not the only reason. Another reason is that gas chimneys, fluid escape pipes, and also diffused gas clouds are common geohazards above or below most petroleum reservoirs and in some CO2 storage sites. Seismic chimneys and pockmarks have been interpreted from seismic data covering several potential carbon storage sites, including Snøhvit in the Norwegian Sea and Sleipner Troll, which is close to the Aurora site, Golden Eye, P18. And this image is from Sleipner CO2 storage site. It shows several chimneys and pipes in the vicinity of Utsira formation where CO2 is injected. And even inside the CO2 plume, we see several, and it's still not known how these pipes appear. Seismic surveys that were done before injection didn't show any pipes. So the question, could this have been formed during injection, or were they there before injection and we just didn't see them? And what is their actually significance? How do they help CO2 injection? Because we know that Sleipner storage site that has very good injectivity, and maybe in part it's attributed actually to these features that it allowed CO2 to propagate into a broader area that was maybe originally thought. However, the process driving the formation of such structures is fully understood, as are the time scales associated with their growth and their role as long-term preferential fluid migration pathways in sedimentary basins. So what we want to know, and the questions that we try to answer in our research, is how do chimneys form? What is their geotechnical significance? Are they leakage pathways? Do they help injectivity and good properties, good reservoir properties? So when we look at chimneys, we first of all think about the mechanisms by which they're formed. And in principle, what we know is that pressure buildup in the reservoirs and source rock might eventually cause failure of the rock, which leads to formation of chimney structure. Geomechanical properties of the host rock and stress state determine the exact mechanism of formation, and which mechanism that could be. First, in hard, brittle rocks, it can be hydraulic fracture. And this is an image of a typical hydraulic fracture. This is a planar structure. And yes, indeed, we see in many cases planar structures like faults and some chimneys that associated with fault, and we see fluid leakage going along the faults. There is fluidization process, which happens in granular media. And here is an example from laboratory experiments done at the University of Oslo when they injected air into the sandbox. And depending on the speed of the injection, different structures were formed, and eventually it was fluidization when solid particles cannot support shear stresses anymore, and they start just to blow. Another mechanism that was proposed for formation of chimney structures is porosity waves. And porosity waves, they produce these really nice, nearly cylindrical structures, which can be quite complex in their morphology. There can be some different branches of these channels. And porosity waves, they are formed in soft and porous rock. So the important parameters here would be the viscosity of the rock and stress dependence of the permeability. And that's why we go to the lab and we check actually what are the properties of the rocks and what is their permeability. And indeed, we see in our experiments that most common reservoir rocks, such as limestone, sandstone, shale, they all creep, so they have these viscous properties, time-dependent deformation, and they have a stress-dependent permeability. So in principle, all these rocks can eventually sustain this mechanism of chimney formation. And very important, of course, why in some places we see chimneys, in some places we don't see. Of course, it's a stress state in the rock, and also which of these mechanisms will happen also depends on the stress state. This more diagram, maybe some of you familiar with it. These circles, they show the stress state in the rock, and these lines, it's so-called failure criteria. So when we increase fluid pressure, our stress state, it moves closer towards failure envelope, and depending on where it meets, it can be shear failure with a shear fracture, or maybe also with porosity waves, because they also actually coupled with this fracturing process, or it can be a tensile fracture and usual hydraulic fracture, or open mode 1 fracture, as we call it, can be created. And a fluidization, it actually corresponds to this one narrow point on this diagram, is when shear stresses are equal to 0. So the next thing we do, we go to the lab and see if we can reproduce creation of chimneys in the lab. And there were a lot of experiments done at different places. People injected air, or people injected water, but mostly it was air, into different granular materials, such as sand, such as compacted powder, glass beads. We chose a different approach. The problem with glass beads and sands that they reproduce elastoplastic mode of deformation. So we wanted also rock or our analog material exhibit time-dependent behavior. So we chose beads which exhibit exactly those properties. So they have this viscoelastoplastic behavior. So they can deform themselves, these particles. And then we inject fluid through this nozzle and see what happens. So fluid propagates upwards, it forms channels, and very interestingly, it also makes these pulses, fluid pulses. You see, it's not just a one stream, constant stream, as we usually observe when we inject into the powder or when we inject into the glass beads. When fluid is injected, it creates actually these bubbles or blobs. And this is exactly what porosity waves are. And then we go to computers and we try to reproduce our experimental results in simulations. So the setup looks exactly like our experimental setup. We inject here. The white arrows here show how the solid particles move as our fluid propagates upward. And colors more or less show this is porosity and the fluid that propagates upward. And in this plot, what we see is a deformation of the surface, of the free surface. It's done separately so that we could compare a deformation of the free surface in our experiment and in our numerical experiment. So why fluid moves here? It moves because of buoyancy. Of course, the fluid in itself is lighter than the whole aggregate of the solid material together with the fluid. But it's not only buoyancy, it's also compaction of the particles and movement of the particles that contributes to generation of this channel. So we don't create here one big fracture, as we saw on another slide, but when our particles allow to deform, they actually produce this nice channel. And here, 3 snapshots of this channel created in our experiments. And here again is the simulation results. Our simulations show that indeed fluid tends to propagate in pulses, and all the next pulse goes through the channel already created by the first pulses. This is a mechanism so-called porosity waves. But how are these 3 different mechanisms are related to each other? Is it in some rocks hydraulic fracture is preferential, in some rocks fluidization, and in some porosity waves? Well, yes and no. In fact, all 3 modes can coexist in the same type of rocks depending on the conditions, depending, for example, on the injection rate, dependent on the fluid pressure. And here is again example from our lab experiment, where we inject the same fluid, and first it's a nice pulse, something that resemble, first of all, porosity waves, but then something else starting to happen. We see there is a lot of deformation around. We see that plastic processes, obviously, and not just flow localization, but deformation localization starts to happen here. So rock starts to behave like brittle rock, like fracturing. So these pictures we usually see in experiments where when this conjugate set of fractures is formed. And then what happens next? We created a lot of different fractures, and then suddenly our material cannot support shear stresses anymore, and it starts moving. You see this convection starts. And actually what we create fluidization that you will see in a moment. Yes, a lot of fractures that are already visible, and new fractures. Here comes fluidization. And quite energetic burst. And when all of this done, we see again nice solitary porosity waves are formed down there, pulsating flow. So all 3 mechanisms here, fracturing, fluidization, and porosity waves in one experiment. So all 3 of them can coexist. They don't exclude one another. And what do we do with this knowledge? We go to the field and try to explain some observations. Now I will show results from multidisciplinary study integrating advanced seismic processing techniques with high-resolution simulations of geological processes that we did with our partners MOL Norge and DGB Earth Sciences. Our study area is a Ringhorn oil field in the central part of the North Sea over the Heimdal Terrace and Utsira High. So you see this is Utsira High, and Utsira is something that always come to my mind. The next thing is Sleipner CO2 storage site, so it's approximately in that area. We identified chimneys using a set of multidimensional seismic attributes that highlight these features, as you can see in this image. So this is a usual seismic image, but green colors is actually already post-processing, where we show where the seismic chimneys are located. And this is a 3D image of the whole field with yellow colors, again showing seismic chimneys and gas clouds. But when we actually zoom in and look a little bit closer at the gas clouds, we see that they are formed by smaller individual chimneys that just cannot be resolved due to poor seismic resolution. So if we would be able to take seismic images with high resolution, we would probably see the individual chimneys when we see gas clouds. And what we do, we created a geological model of the area. We chose one 2D profile that has seismic chimneys. We identified which geological sequences are present there, and did simulations. Here, the initial condition, we have just a reservoir filled with fluid flow, and here we know that there is some deeper anomaly present and in the area. That's why we included it here, deeper anomaly. And we don't impose anything else, just this reservoir with fluid that is, of course, lighter than the surrounding rock. Therefore, fluid wants to flow upward. And we just allow fluid to do that and see what happens. Fluid indeed starts propagating upward, but when it propagates, it doesn't flow just as a diffused cloud. It has a tendency to form these channels. So localized fluid flow. And at the top, we have another geological layer with different properties that actually doesn't stop propagation of chimney, but it changes slightly the size of chimney. It does stop smaller chimneys here, but the bigger chimneys, they still could propagate through the second layer. And porosity of fluid channel, it's about 15%, is up to 2 times higher than the background porosity. We see that fluid propagation is mostly vertical, which is driven by buoyancy of the fluid. And the most interesting here is the time scale of such fluid propagation. It's actually just a few months. So if you think about it, leakage from reservoir can take just 3-4 months. And we know that, for example, that was an episode of leakage at the Tordis field, where they injected wastewater, and then they saw new seafloor crater forming in the area of injection of wastewater just after 4 months after injection. Yes, it can be that fast. And we know also that at Sleipnir, they made a second seismic survey after 2 years of injection, and they already saw the seismic chimneys. So in principle, those 2 years was enough. And here is a comparison of our modeling result with this data. Again, yellow colors on both figures indicate identified seismic chimneys here, and in images below, there's some modeled seismic chimneys. Size and time of chimney propagation depend on material parameters of the rock and the fluid. Of course, in shales, chimneys will be propagating or forming much slower than, for example, in sand or in limestone, but it's still possible. And another thing that we see in these simulations is that gas clouds often comprise distinct channels, like here. On the image here, we see more or less gas cloud. We don't see separate chimneys, but in the simulations, we do see that all of them are separate chimneys. And of course, how the chimneys look or where they exactly be located depends on geological complexity. It depends on the topology of the reservoir. It depends on the topology of sill, depends on the topology of any upper layer. And here and material parameters, of course. Here we did several simulations just with a simple synthetic setup where our reservoir has just sinusoidal shape, and so where the chimneys will be originated. And we see the chimneys start from the topological highs here. And here we varied wavelengths of the sinusoidal reservoir, so it's a different geometry, and we see that actually the pictures are quite different depending on the reservoir geometry. And these two cases, they have a similar reservoir geometry, but different material properties. This layer was for rock, which is more brittle. And chimneys, they do look different porosity, different amount of the flow. And in this case, we included also a competent layer above the reservoir and a weak layer above the reservoir. And we see that while these layers, they don't stop the chimney propagation, they do change their size and porosity inside the chimneys. But what about dykes and sills? Can we explain how these are formed? Well, this is a model that reproduces formation of dike and sill complex. In this case, we have a source of fluid. It can be, for example, hotspot and melt forming due to it. And above, we had a tight rock, some sill. And let's see again what happens. A melt that contained in this region propagates upward, creating dike. Then it meets this sill and it flows around it, forming this nice sill structure and dikes again at the ends. But also eventually melt was able to kind of go around, penetrate through the sill, and another dike was able to form even inside the sill area. And how do we do it? How do we model it? Of course, very important is numerical technique. The important thing here is high performance computing. With simulations like that, we don't prescribe where our channel will be formed. We don't prescribe fracture, as it's very often is done in the model. Yeah, you see in the seismic data, you see that there is a fault there, or you see that there is a chimney there, and then you go and say, yeah, I will put fracture here because I see there is a chimney there. No, we don't do that. As you saw, our initial conditions, only reservoir, as only data about reservoir and about caprock. And that means that we don't know in advance where chimney will start. But resolution of which chimney, its visualization, requires very high resolution. So that means that we need equally high resolution through the entire computational domain. It needs really, really high resolutions. In our recent paper published in GCubed, we ran 600 nonlinear simulations on a resolution which was 1000 by 3000 cells in 2D models. So it's a huge resolution. And we were able to do that in a normal human lifetime. So how do we do it? We use advanced computing and graphical processing units. This is the same equipment that is used for computer gaming. So GPUs, they were actually designed first for computer gaming, but now they're actively used in AI, they are used in creative production and in high performance computing. And we use frontier simulation techniques, finite difference methods, supercomputing on GPUs, and massively parallel iterative solvers. And now we have one GPU here at IFE. We just installed it, and we will start simulations on our in-house computer. So that was all from me. Thank you for staying.